Now, what I've given you here is a lab that has some background information. And that background information shows how I calculated the theoretical value of the molar volume. We know that the molar volume of a gas at STP is 22.4 liters, right? Well, if you look, based on PV equals nRT, okay, PV equals nRT. If I have 1 mole of the gas, my gas constant is 0.0821 liters times atmosphere per mole times Kelvin. My temperature is 273.15, right? Because that is 0 degrees Celsius, which is standard temperature. What is standard pressure? 1 atmosphere of pressure. So when I put those values together and I calculate the molar volume, it came up with 22.4 liters. Now, at the bottom of that background information, it says about Dalton's law of partial pressure, doesn't it? The total pressure is equal to the addition of each one of the parts, whether there's 1 part, 2 part, 3 part, 4 part, 5 part. It could go on and on and on, etc., etc. Now, if you look on the back of that page, it gives you a chart. Notice what the label of the chart is. What is it? What's the label of the chart? Millimeters of mercury. So it's a different chart than the examples that we worked earlier with Dalton. Okay? And the final thing down at the bottom. The final thing down at the bottom is the combined gas law. Now it says P1 V1 over T1 is equal to P2 V2 over T2. Whereas anything with the subscript 1 represents conditions that you measured during the experiment. Variables with subscript number 2 are at STP conditions. To get the molar volume at STP, divide the value of V2 by the moles of the gas N that are produced in the experiment. So what we're going to do, and we're going to do this period and a little bit into next period, is we're going to do an old lab that I used to do in here. And it's given right up here. A butane lighter, and you have this on the back, on the next page. A butane lighter was used to collect the gas using water displacement. The amount of butane, which is C4H10, collected was 500 milliliters. So I collected 500 milliliters of butane based on water displacement. The mass of the butane collected was 1.22 grams. What I did is I took the mass of the lighter beforehand, collected the gas, and then took the mass of the lighter again after it dried. Okay? And it gave me 2.2 grams. The water temperature was 23.5 degrees Celsius. That's going to come into fact. That's going to come into play when I need my chart. Okay? The water temperature was 23.5 degrees Celsius. The barometric pressure in the room was 28.587 inches of mercury. Now, it says inches of mercury, doesn't it? What's my chart? What was my chart we just discussed? Millimeters. Okay, so we're going to have to do some conversions there. Now, when you do this lab tomorrow, you are going to have to find the barometric pressure. Let me show you how I do that. I go to this neat place. It's called something we know as the internet. Okay? as I'm on the internet, I click onto this and it says OK. All right, go ahead and update me. I'm going to click on this. Here is Saline, Ohio, the Weather Channel. Okay. Now, as I look at Saline, Ohio, the Weather Channel, right now, it's telling me that the pressure is 29.63 inches of mercury. So when you do your lab tomorrow, you're going to have to get on the Weather Channel and check out what the barometric pressure is. All right? But it's not too hard to do. Not too hard to do. Now, as I come back to my problem, it says, based on these measurements, follow the steps below to calculate the volume that 1 mole of butane gas will occupy at STP. All right? We know what it should theoretically be, don't we? What should 1 mole of butane gas at STP be? 22.4 liters, right? Okay, that's what it should be. Well, I'm going to go through some steps to calculate this, and it's important that you follow along with me. Folks, this is going to be what your homework is. This is going to be the lab tomorrow. This stuff right here that we are doing. So, as I start out, it says, convert the temperature of the room to Kelvin. Well, it said that we had 23.5 degrees Celsius, right? How do we get that to Kelvin? How do we get that to Kelvin? We add 273.15, right? So my temperature in Kelvin is going to be 296.65. My second step, okay? My second step is to convert the barometric pressure of the room to millimeters of mercury. Do so using the following two methods. What I'm going to do, we're going to get a bell here in a second, but we're going to convert, I'm going to convert this in two different ways, just to show you two ways in which you can do it. Now, it doesn't matter which way you use, okay? Doesn't matter to me which way you use. But as I'm doing this, I say, okay, what is my pressure in inches? 28.587. 28.587 inches of mercury, right? Well, as I do my conversion box, I want my inches to cancel, so I know that 1 inch of mercury is 2.54 centimeters of mercury. My inches cancel. So basically, I'm taking that 28.587 and I'm multiplying it by 2.54, and I get 72.61098 centimeters of mercury. Now, I've converted this to centimeters of mercury. All I need to do to get it to millimeters of mercury is jump it one place to the right. So, if I'm converting this, it is 726.1098 millimeters of mercury. Now, the second way to do it is a little bit easier, I think. Okay? So what I'm going to do is I'm going to take that same value, the 28.587, inches of mercury. And my conversion factor now, and all I did is I found this on the internet, or I knew it, okay, that 29.92 inches of mercury has 760 millimeters of mercury. So my inches of mercury cancel. When I do my math for that one, it comes up to a value of 726.1404, and my label is going to be millimeters of mercury. So if you look, those two values, 126.1098 millimeters of mercury, and, well, I said one, it meant 726.1098 millimeters of mercury, 726.1404 millimeters of mercury. So they're very, very close, whichever way I did it. All right. So I'm going to save that for a little bit later. I'm probably going to use that blue one there, the bottom one. Now, my next question, number 3, says, at 23.5 degrees Celsius, the vapor pressure of water is 21.7 millimeters of mercury. See Table 1, vapor pressure of water. Now look at your vapor pressure of water, okay? Look at your chart. At 23.5, would you agree that it's 21.7 millimeters of mercury? All right, so my total pressure is equal to the pressure of the butane plus the pressure of the water. Well, I just figured my total pressure, didn't I? So I'm going to use that, total pressure being 726.1404 millimeters of mercury equals the partial of butane plus 21.7 millimeters of mercury, because that's water. So when I came up with my value, I'm going to take the 726.1404 and I'm going to subtract 21.7. So the pressure of the butane gas is going to be 704.4404 millimeters of mercury. Once again, how did I get that? I took the 726.1404 and I subtracted 21.7 millimeters of mercury. Now, number 4. Problem number 4 says, convert the volume of gas to liters. Well, in my original problem, how much gas did I collect? How much gas did I collect? If you go back and look at the start, it says 500 milliliters. Well, if I convert that to liters, what is that? 0.500 liters. Now, here's where we're getting into some of the good stuff. Okay, we're getting into some of the good stuff. It says, use the combined gas law to calculate V2. Well, you had the whole combined gas law given to you, but when I solve for V2, I'm going to solve for V2. V2 is equal to P1, V1, oh, not VI, P1, V1, T2 all over T1, P2. How did I get that? I manipulated the equation, okay, to solve for V2. So V2 is equal to P1, V1, T2 all over T1, P2. Remember that the 1s were the one I did in the experiment. The 2s were the STPs. Now, all I'm simply going to do is fill in values. I just calculated the pressure, and that was P1 was 704.4404 millimeters of mercury. My V1, I collected 5 liters, or 0.5 liters, right? What was my T2? Well, T2 is standard temperature, right? Because all the 2s are at standard value. What's my standard temperature? In Kelvin, it is 273.15 Kelvin. That's on top. I divide that by T1. T1, I need to go back to the very initial problem, problem number 1. My T1 was my experimental temperature, which was 296.65 Kelvin. And I multiply that by P2, which is standard pressure. Now, ladies and gentlemen, I cannot use 1 atmosphere of pressure. Why not? Why can't I use 1 atmosphere of pressure? That's our normal STP. Anybody know why? Huh? Well, it's at STP, what we're calculating it is. But what was the pressure that we calculated for the top one, P1? Look at that label. It's in millimeters of mercury. So I have to know the millimeters of mercury. Well, I just so happen to know that at standard temperature and pressure, that in millimeters of mercury, standard pressure is 760. So standard pressure in millimeters of mercury is 760. If I go through, I have Kelvin on the bottom, Kelvin on the top, millimeters of mercury, millimeters of mercury. So my label here is going to be liters. So when I do my calculations, I come up with a value of 0.42673 liters. So that is equal to V2. So that is my volume at STP of the gas I would have collected. Now, as I scroll down, I'm not done yet. How many moles of butane were collected? Well, if you remember right, I told you that I took mass before and mass after of the lighter. So I'm going to flux capacitor this to get it into moles. Because I can calculate the molar mass of butane using my periodic table. That value is 58.1222 grams of C4H10 is equal to 1 mole of C4H10. I get my grams to cancel. I do my math, and I know that this comes out to 0.0200990, and that's moles of C4H10. Moles of butane. That's just a flux capacitor move. Now here's the big final ending. The final ending. It says, calculate the experimental molar volume in liters per mole by dividing the liters of butane gas. What was my liters of butane gas? Look at number 5. What was my liters of butane gas? 0.42673 liters, right? What were my moles? 0.020990. So when I calculate that, I'm going to put it into 3 significant figures. I get 20.3 liters per mole. What should my theoretical value at STP be for butane gas? 22.4 liters. So that's not terribly far off, is it? Could I calculate my percent air? Absolutely. Absolutely I could. So that's not terribly far off. Now save that paper, save all those calculations. Your homework is going to be very similar to that.